Well, last time we had Kirchhoff's voltage law, and that had to do with walking around in circles, closed loops, and it had to do with voltages, of course. Now we look at Kirchhoff's current law, which has to do with current, or amps, of course, and it occurs or it applies to junctions. At any junction, here's a junction. See where the wires come together, where you have to put like a little bit of solder or whatever? That's a junction. So at any junction, the total flow, and by flow I mean current, amps, the total flow that goes into the junction has to be the same as the total flow that goes out of the junction. Okay, it's just like if you had water in pipes and there was like no air in the pipes, right? If you had water in pipes, if you had 2 gallons going in one end of a pipe, you have to have 2 gallons going out the other end of the pipe. Again, there's no bubbles or anything, so it has to be so. So, with that as our basic idea, what goes in must go out, we can do things like, here's a nice little junction. So what is this current X that we've got here? What is it? Well, I'm going to do it the official way. I'm going to say what goes in is the same as what goes out. This is the official math way. What goes in is, and you look at this junction and you say, what's coming in? Well, I got 2 amps coming in from the top there. 2 goes on the input side. I got 5 more amps in coming in from the bottom. So add 5. 2 plus 5 is coming in. And then this X here, well, that's going out. That goes over here on the equals out side. And so very quickly, we have a nice solution. X must be 7. I'm assuming these are amps. 7 amps. Now you might have been able to see that just by, looking at this, straight. You say, well, these are both going in. 5 and 2 is 7 going in. They're both going in. And so they join together and they have to leave, right? You can't just have current all going into something because where would it go? There's no place to go. It's something's going to come out. It's kind of like a house of horrors. So this is my house of horrors, okay? So what you have is a bunch of people and they're all shoulder to shoulder in the house of horrors and there's just no more room for any people. And then what you do is you take a person over here and you push them in. What's going to happen over here is this guy is going to pop out, right? What you push in, because it's shoulder to shoulder, one has to pop out. If you were to pop 2 in, boom, 2 go in, guess what? 2 are going to have to come out. Okay, so what goes in must come out. It has to. It's like a house of horrors. Meanwhile, hopefully this one's not so scary as a house of horrors. Let's see what we got here. Well, you can try to look at it and try to make sense out of it, or you can just be methodical and always say, look, what goes in equals what goes out. And what's going in? Well, X is coming in, so I can put the X on the inside, on the left. And then I got, well, this 2 is coming in. It's coming in where? It's coming into this junction, right? This is the junction. So X is coming in, 2 is coming in, and then just make sure, what's this 5 doing? Well, it's leaving the junction. It's on the outside. So the X plus 2 is coming in, the 5 is going out. And that's not a bad equation, certainly not compared to some of the other equations we played with. Do the old subtract 2 on both sides trick. X must be 3 amps, I presume. And again, you can take a look at it for a reality check and say, you're telling me this is 3? So you're telling me that 3 comes in, 2 comes in? 5 must go out. Has to. So it's real easy to check your answers to these things too, so not a bad habit. Let's come down to this one. What's X? See if you can figure it out just by looking at it or maybe even writing out the equation. I'm going to write out the equation just because. And I'm not going to keep writing in equals out. You know what I'm doing. I'm saying in equals out. So what's coming in? 18's coming in, and that's the only thing going in. 18 goes in. What goes out? That's leaving. That's leaving. Remember, I'm talking about this junction here. So the X and the 2 are both leaving. They're going out. So 18 in, X plus 2 out. What is X then? Well, it looks like I have to subtract 2 on both sides and get 16. X is 16. And again, you want a reality check, just put a 16 here and see if it makes sense. Leaving, 16 and 2, that's 18. So there must be 18 coming in to replace it, so to speak. What goes in must come out. It all works. You're starting to get the idea? What goes in must come out. Here's a junction. Now this is going to be kind of a funny case. What goes in must go out. Okay, well, what's flowing into this junction? Not that, not that, nothing. Kind of a weird situation. Nothing's flowing into the junction, huh? That's what you're telling me? Okay, well, math doesn't lie, so nothing's flowing in. It's all flowing out. I got x going out, I got 14 going out, I got 12 going out. So what's my equation look like? Well, if I combine my like terms over here, 14 and 12 makes it 26. And then I should subtract 26 on both sides to get the x all by its onesies. Remember, keep the equations sides separate. And so 0 take away 26 is negative 26. And so x has to be negative 26. And what does that really mean? Well, the way it's drawn, which is going to the right, it's a negative number, negative 26. That means in reality, the current's going that way. You would have basically two choices. You could either leave the arrow drawn the way it is and call it a negative 20, call it a negative 26. That's one thing you can do. Another thing you might do is erase it. Well, not there, I guess. Is you might erase all that stuff and let's use a different color. Maybe reverse the arrow and then you could call it a positive 26. I'd only do that if I didn't have this current showing up in other places in my circuit analysis. It's probably easier just to leave it as a negative 26 and then just say to yourself, you know that negative current? Yeah, that's because it's actually going the other way. It's no big deal. Not from an algebra point of view, it's no big deal. So what goes in must go out. So that was playing with just numbers. We were able to solve and get a number. Sometimes you can't quite solve and get a number because, well, like I've got an x and a y. There's two currents that I actually don't know. And if you only have, or I should say, if you have two currents that you don't know, you're not going to be able to solve for both of them just by looking at this, what goes in, what goes out. Because what goes in? Well, let's see now. What goes in? X is flowing in and the 2 is flowing in. The inside of my equation is x plus 2. What's going out is the y. And so the x plus 2 equals the y. Now we're asked to find y. Yeah, we just did actually. Y is equal to x plus 2. And you can't do anything better than that because you don't know what x is. Maybe someday with a different equation you'll solve for x, and then once you know what x is, you can come back to this equation and get y. But for now, that's all we can say. Y is the same as x plus 2. Why don't you try all three of these? Three of these? Why don't you try all three of these yourself real quick, like? See what you get. Okay, here we go. Maybe I'll just highlight what comes in. It might be easier. Y goes in. And that's the only thing going in. So Y goes in. Everything else goes out. I got X going out. I got a plus 2 going out. They wanted me to solve for Y. Well, I did. Y equals x plus 2. So how do you like that? This and this have the same solution for y. Here, y was leaving, x and 2 are coming in. Here, y was coming in, x and 2 were leaving. So it's kind of the opposite, but y is equal to the same thing. What do we got here? Coming into the junction, right? So here's my junction. Coming into the junction is x. And that's the only thing coming into the junction, x. Equals, and what's leaving is both the y and the 2 are both leaving. Now again, we're wanting to solve for y, which means get y by itself. So if I want y by itself, it looks like I'll have to subtract 2 on both sides. Keep your sides separate. So I've got an x minus a 2 on this side. Remember, those are not like terms. They don't go together. One's an x term, one's a number. They don't go together. So x minus 2 is the left side equals y on the right. We're moving now. Okay, here's another one. What comes in? Well, that's going in. That's going in, right? Again, we're talking about this junction right here. So I got two flows going into the junction. I've got a flow of X going into the junction. I've got a flow of Y going into the junction. That's my total going in. Leaving is 2. Once more, we're asked to solve for Y. So it looks like I actually have to subtract X on both sides. See, here's the Y. I want that by itself. Somebody added X. You take that back. You subtract X. So the left side is now just Y by itself. And the right side, you can write this two ways. You can write this as 2 minus X, because that's what it says. It says take 2 and subtract X. That's what I did. Or, if you really want, I'll say or. You could say, well, I'm going to put the X term first and then the constant next. So the negative X goes first, and then you've got plus 2 going next. Okay, it means exactly the same thing. You paying your money, you take your choice, right? Page 2. Solve for X. Well, it's the same old Kirchhoff's current law. Where's the junctions? Well, the junctions are basically where the wires meet. Here you've got wires meet. Here you've got wires that meet. You wouldn't really call that a junction. I mean, technically you can call anything a junction, really, but no, that's just all the same wire. So the thing to keep in mind here is that this X that we've got here flowing, it's the same X flowing here, flowing here. It's all the same X. It's even the X over here. This is X coming around the corner. It's all X. It's X for this entire branch. That is a branch. Branches are separated by junctions. So here's where the junctions are. So between there and there is all one branch. If you wanted to come over here, this is all one branch, right? And notice it's all, I guess I'll use the same color. It's all 12 amps. 12 amps going this way, 12 amps going this way. It's all 12. And it's all going the same way, right? Make sure you've got the 12 going this way, coming around this way. And then we've got this branch here. Ooh, different color, please. Let's see, what can we do? We can do sort of gray, I guess. This is a third branch. And so we've got 3 amps, or whatever these are, going down the middle branch. So we have 3 branches. That's worth writing down. 3 branches. 12 in the left branch, 3 in the middle branch, X in the right branch. Pick a junction. And it doesn't matter which one, you get the same answer either way. I'm going to pick that one. I'm going to call that junction A. What goes in? Well, 12 goes in. Boy, need more colors here. I got this 12 coming into the A junction. I got the 3 coming into the A junction. Those 2 flows are going in to the A junction. So I got a 12 in and a 3 in. X is what's going out. And so guess what? We just solved for X. X must be 15. This must be 15 amps right here. Now if you want, what you can do sometimes is you can say, well, let me come back to my circuit. You're saying that's 15, so you're saying that this is 15. Let me look at this other junction for a second here. What does this other junction give me? It tells me 15 goes in, and then both the 12 and the 3 go out, and look at that, it checks. We did it right. You can always check at the other junction. It should be true for all junctions everywhere in your circuit. Total in is the total out. Let's look at this one. Let's see now here. I'm going to use this orangish flavor. So notice this 20 amps. Where's that? Well, that's 20 amps here, here, here. It's all 20 amps until you get to a junction. And you can follow it backwards too. This must have been 20 amps, 20 amps, 20 amps until I got to this junction. So all of this is 20 amps. If it's 20 going this way, it must be 20 going up, which means I got 20 coming into this junction. If it's 20 going this way, it must be 20 coming down, which means it's 20 coming out of that junction there. That's all 20s. Now we got this 5, of course, and that 5 will be from this junction all the way to here. That's all 5, and that means that this junction has 5 going this way, And over here, this has 5 coming in, right? It's all the same flow for that whole junction. And then finally, this is all X amps. Oops. Fine, you. No, not that one. This one. This is all X from junction to junction. That's all X, which means I've got X coming out of this node, and I've got X coming into this node. Cool. So that's about as labeled as you can get, right? So now you pick a junction. Doesn't matter which one. Pick a junction. I'm going to pick, I don't know, I guess I'll pick this one. I'll call that my junction A. So at junction A, what goes in must come out. Something like that. Anyway, so what's coming into junction A? We've got, well, what was that? That was X. We got X coming in. We got 5 coming in. We got X and 5 coming in. X and 5 coming in. That 20 is going out. So what's this telling me? It's telling me that X must be, you subtract the 5 on both sides, X must be 15 amps. So now that I wrote all that scribble stuff all over this thing, you may have this in your notes, or besides, you can rewind. I'm going to get rid of that now, and just try to take another look at this. From here to here, I got 2 flows going to the left, and again, we know that this must be 20 coming in and 20 coming out. Don't those 2 flows, that's a parallel arrangement, right? Don't those 2 flows have to add to 20? X and 5 must add to 20. After a while, you just start to see these things. I got 2 pipes to the left and 1 pipe to the right. So the pipe to the right is 20. The 2 pipes to the left must be 20. So if that's 5, that other one must be 15. Okay. So I encourage you to try to, use your physical reasoning, so to speak, for some of this stuff, at least to try to make sure that your answer seems reasonable. The algebra is the most reliable. Physical reasoning, you can kind of get things backwards. I do it all the time. You just look at something and say, oh, that's like a negative 15. Yep, that's what it is. And then you're like, oh, wait a minute, that was a positive 15. Darn. If you do it the algebra way, the algebra is usually safer. That's why we have algebra. It makes things safer. Well, we're looking at the bottom example here. We need X. Okay. I guess I can't quite do that same intuition thing because these are going in different directions. Oh well. Well, good thing we have algebra. So what should we do? I know what I'm going to do. I'm going to get a blue pen. See that 12 there? That 12 is the same as the same as the same as the same. This is 12 coming into this junction. I'll call that my junction A. Doesn't matter which one, but I'll call that one my junction A. It's got 12 coming in. You can see it's got 7 coming in, right? And then this is what's going out. So at junction A, what goes in must go out. Coming into junction A is the 7 and the 12. Going out is the X. So guess what? X is 19. Has to be. And if you wanted to try to make more sense of that, you could say, well, what's happening here? You could say, well, what's happening here? You could say, well, if I look at the other junction, I got 19 going in, and then this 12 came from over here, so that must be 12 there, and then this 7 comes from over here. And notice I got 19 in, and I got 12 and 7 is 19 out. Everything checks. Checks fine. Okay, what do we got here? How many more of these have I got? Okay, one more page. All right. It says solve for x, then y, then z. And this is kind of just because it'll work, that's why. In general, you don't have to solve for x and then y and then z, but it'll work nicely here. And why do I say that? Well, just watch. Watch this. This is going to be cool. If I want to solve for x is here. I have to look at either this junction or this junction, right? You have to look at a junction that x connects to. Now, I don't want to use that junction because that junction I have a y, and I don't know what y is. I won't be able to solve for x if I have a y in my equation. So I'm going to use junction A. And what goes in must go out. this is coming in, right? If you were to follow this around, I got 18 coming in. And that's the only thing coming in. So now what's going out is the other two things. I got x going out, right? Right there, the x is going out. And this 8 is coming out as well. So 18 equals x plus 8. Okay, subtract 8 on both sides. So x must be 10. There it is, x is 10. So I think what I'll do now is I'll erase some of this stuff and I'll just kind of label this. Oops, I'll use a real pen and I'll label it 10. X is 10. Woo. Now, switch colors. Let's go get y. Now here's my current y. To solve for y, I have to play with either this junction or this junction, a junction that y hitches up to. And same as before, I don't want to use that junction because that junction has a z. I don't want to play with z right now because I don't know what z is. So I'm going to come up here and do this junction then. So let's play with junction B then. What goes into B? I'll tell you what goes into B. This goes into B. It says X, but it's 10, right? We know what that is. 10 goes in. What else goes into B? Well, if you follow this 3 around, the 3 goes into B. So I got a 10 plus a 3. Those both go into junction B. And then what leaves is Y. And so Y must be 13. Boy, that wasn't so bad of an equation. Y is equal to 13. Let's replace that right there. This is a 13. Cool. Now we can solve for Z. So let's use a cool color. I don't have any more cool colors. Darn. Let's use that one. I want to solve for Z, which means I should either use this junction or this junction. Now in this case, it doesn't matter which junction I use because I don't have any other unknowns. Z is the only thing that hasn't been solved for yet. So it really doesn't matter which one I solve for. Maybe I'll use junction C just to be different. So what goes into junction Z? Well, what goes into junction C? I'm sorry. Well, this Z current is coming into junction C. Oh my gosh, tongue twister. And this 8 is coming into junction C. So that's what's going in. What's going out? Well, see, this is leaving, right? The 18's leaving. So that goes on the other side. And so you subtract 8 on both sides. And you very quickly get 18 minus 8. Z is also 10. So X was 10, but guess what? Z is also 10. And now I'm going to show you something interesting. So we've been saying, or I've been saying, that this Kirchhoff current law applies to junctions. Well, you can make a really big junction. Try to picture all of this part of the circuit. I wonder if I can shade that in somehow. I don't really see how. Anyway, just picture all of this shaded in. I don't have a paint bucket tool. Are you serious? Anywho, think of this as a really big junction. Well, then what's going in to the junction is 10, and what's coming out of the junction must be the same. The 10 going in at the top must be balanced by the 10 coming out the bottom. Now, ain't that something? So that's a handy little trick that you might use sometimes. You could have like amazingly complicated circuitry over here. You're like, who knows what's going on over here? Let's put some transistors or whatever. We got all kinds of stuff going on over here. You could have the most amazing circuit in the world, but if it only has these two places where it hitches up, here and here, then if you got 10 coming in over here, you must have 10 coming out over here. Just think of this as a big junction. So that's a cute little shortcut. Okay, let's see. Solve for X, then Y, then Z. Oh, this is a challenge you should try. You should try this yourself. Go in order, X and then Y and then Z, and let's see what happens. Well, if I go X first, well, I should use one of these two junctions. And I don't think I'm going to use that one because that one's got Y's, it's got Z's. Eesh, too complicated. I want to use this junction, which has X's, it has 3's, it has 10's. Now that's more like it. So what's coming in to junction A? At junction A, what goes in must go out. What's coming in is, well, let's see, what's coming in? Well, the 10's coming in, right? Because it comes around this way. So I got 10 coming in. But the 3 and the X are both leaving. They're leaving. So those are going to go on the outside. The X and the 3 are on the outside. Subtract 3 from both sides, and we very quickly find that X must be 7. Cool. So let's get rid of this stuff. It's all just kind of in the way, right? And just label that. That's 7. That was fun. Really it was. Now let's find Y. Well, to find Y, again, I have to use one of these two junctions. And I'm going to stay away from this junction because it's got a Z. That's no good. So I'm going to stick over here to this junction. I'll call this junction B. Doesn't matter what you call it really, but I'll call it junction B. And at junction B, what goes in must go out. And what's coming in to junction B is the 5 is coming in and the 3 is coming in. So we got a 5 coming in, we got a 3 coming in. That Y is going out. So actually, just add the 5 and the 3. Y must be 8. That wasn't bad. This is 8. Now let me get rid of this, and now we'll solve for current Z. We have to use either this junction or that junction. It doesn't really matter which one. Oh, I think I like this junction down here. It looks fun. So let's see now here. Coming into junction C is both the 7 and the 8. Leaving is the Z. I think you can see what the solution is. 7 plus 8 go in, Z comes out. Z must be 15 amps or whatever these are. What goes in must go out. Use the algebra. And our final example. Ooh, that one's got some stuff to it. Well, if you go X and then Y and then Z, it's actually, well, it's not that bad, I don't think. Let's try. I want to solve for X, means I should use one of these two junctions. Again, I don't want to go over here yet because that's got Y's and Z's and all kinds of weird stuff. I don't want any of that right now. So I'm going to come over here, I'm going to call that my junction A. So at junction A, what's going into junction A? 18 is going in. And that's all that's going in. 18 goes in, and the rest is going out. I got the X going out, I got the 5 going out. So subtract 5 on both sides. X is 13. So this is a 13 right there. Cool. Let's go get Y. So if I want to solve for Y, I have to go to one of these two junctions, because that's where Y hitches up to. And I don't quite want to use this one because I'd be dealing with a Z that I don't know what it is yet. So I'm going to have to use, or I'm going to want to use at least, that junction. I'll call that my junction B. So at junction B, what's going into junction B? 5 goes in, Y goes in. Those are what's going in. So at B, Y goes in, 5 goes in. Cool. And equals what goes out, and the 4 is what's going out. So actually, I'm going to subtract 5 on both sides. And notice I've got Y equals a -1. -1. That's what it is. It's -1. Now what that means, being negative, is that it's going the other way. Okay, this is actually going this way. But just leave the diagram the way it is. The negative is telling you the arrow's backwards, and I would just leave it as is. You could go fixing things, but then you have to start recalculating things, and it's a mess. Just leave it and say, oh, negative. Oh, well, I drew the arrow backwards. Big deal. Big deal. Now, I want to get Z. So to get Z, I have to come either to this junction or to this junction. Either way, it should get you the same answer. So I'm going to call this junction C, and I'm going to call this junction D. And I'm going to do this at both junctions just so you can see what happens. If I go to junction C, you have to use the arrows the way they're drawn. What goes in must go out. And what I've got drawn here is I've got an X coming in. And that's the only thing I've got coming in. So in is the X, which is 13. The way these arrows are drawn, they're both going out. The Y and the Z are both going out. The Y is a -1, and the Z is going out. So since my algebraic solution's -1, that's what I'm putting in it. So, you know, Y is going out, but it's actually -1, which is going to mean that I'm going to add 1 to both sides. So Z is equal to 14. Like that. Z is equal to 14. Now if you wanted to try at junction D, you'd say what's coming in is the 4. 4 comes in. Actually, the Z's coming in too. What am I doing here? What am I doing here? The Z's coming in, 4's coming in, Z's coming in, and what's going out is, come on you, what's going out is this current. Well, what's that current? Well, you see this 18? What's this symbol? It's not a battery. That's the symbol for ground. It's like the chassis of your car. And this is ground over here. So the thing about ground is, it's a big, giant junction. It's like the whole chassis of your car junction. What goes in must come out. So if I got 18 amps coming out of the ground over here, I must have 18 going into the ground on this side. It must balance. And if that's 18 going in, this has to be 18 here, going out. So 4 plus Z goes in, looking at junction D, and then 18 goes out. Notice you subtract 4 on both sides. And we do, in fact, get the same answer. Z is 14. Ain't that something? I always like that about algebra type stuff. The math always knows. The math knows what's going on. So you might be doing something that looks like it's going to give you a completely different answer, but it doesn't, because the math knows what's going on. And that's part of why we're doing this whole Kirchhoff algebraic stuff. So, okay, today we focus on the current law. Enjoy your problems, Zach.